This lecture follows up on the lecture on pathology of risk and uncertainty. In this lecture, we're going to get into a bit more detail. We're going to look at such things as expected utility and how that affects how the different utility functions that one can specify affect risk and uncertainty. Much of this comes out of the agricultural economics literature. We begin by looking at risk attitudes, and we want to model and manage risk using utility functions. The Nobel laureate Kenneth Arrow observed that individuals display an aversion to risk, they're risk averse, and that risk aversion explains many observed phenomena. So the measures used by economists tend to be expected returns, where there is no risk, and expected utility, where this risk aversion plays out. When we look at the marginal utility of income or of wealth, we find that the linear marginal utility for income implies risk neutral. Decreasing marginal utility for income implies that the person is risk averse, whereas an increasing marginal utility of income indicates that they're risk seeking. And what we want to do is we want to show how that is. So when we have utility here and income over here, and usually we have to have some kind of wealth involved as well, but we'll deal with that later on. So a risk neutral person follows this, has a utility function that looks like this, straight line. A risk averse person has one that rises and then falls, and a risk seeking person follows this green line. So those are the differences that you see in terms of what the marginal utility looks like. And the marginal utility, recall, is simply the first derivative of the slope, of the function, which means it's the slope. So you see here the slope is very steep and then it begins to decline. Here the slope is flatter and it begins to rise, and here the slope is unchanging, which indicates that regardless of the level of income that one gets, there's no change in their risk attitude, whereas with the risk-averse person, the more income they get, the more averse they are to risk. We can also look at complex marginal utility, and that's a case where that function has this S shape, such as indicated here. So in this part, they're risk-seeking, and then they're risk-averse at the upper level as that income increases. So risk-seeking for small sums, risk-averse for large sums. Now, when it comes to risk attitude, and here we get into some formal definitions related to risk attitudes. So we define certainty equivalence, CE, and we denote this double arrow, if you like, as being is preferred to. So if A1 represents some bundle of goods, is preferred to A2, which represents an alternative bundle of goods, and A2 is preferred to A3, then there exists some P, a probability, such that the decision maker, and we'll refer to the decision maker by the acronym, if you like, DM, is indifferent to receiving A2 with certainty, and a lottery of A1 and A3 as follows. So A2 is indifferent to this lottery, where you get a probability P of getting A1 and a probability A1 minus P of getting A3. So A2 then is the certainty equivalent of this particular lottery PA1 plus 1 minus PA3. With a risk-neutral utility function, as we indicated, we get a straight line utility function, which mathematicians say is quasi-concave and at the same time quasi-convex. That means it's concave and convex. So this utility function indicates risk neutrality on the part of the decision maker. So the first derivative, so the slope of this line, is given by k, and it's greater than 0. And you see that with that upward slope. But the second derivative is simply 0. Now with a risk-averse utility function, we get a little bit more complication. So we have this utility function which looks like this, and what we're interested in is a bundle of or an income x1 here, which sits on this utility function, and we get ux1. So the utility of x1 is ux1. The utility of x2 is ux2. And if we draw a straight line between these 2 points, that gives us the expected utility. Okay, but there's a difference if you take the midpoint between x1 and x2, so this average x bar, all right, and the utility of x bar is somewhat higher than the utility of the certainty equivalent, where the certainty equivalent is the mean of x bar, the expected utility of x bar, all right? So you see that here is the expected utility. So if we take the average of x1 and x2, we get x bar. Where it hits this expected utility line, that gives us the expected utility of x bar, and that's the certainty equivalent. Notice that the certainty equivalent of x is less than the mean of x. So we define pi as being the risk premium, which is the difference between the expected monetary value. All right, this is the expected monetary value and the certainty equivalent. So these are the monetary values here. So pi is the difference between x bar and x certainty equivalent. So a strictly concave utility function indicates risk aversion, where the first derivative, so the marginal utility is positive, but the rate at which the marginal utility increases is negative. So the second derivative of the utility function is less than 0. And here x bar is simply, we define it as half of x1 plus half of x2. And the expected utility of any x is equal to the probability of the utility of x1 plus 1 minus the probability of utility of x2. So with risk aversion, utility increases with wealth, but marginal utility mu falls, which implies that a farmer, for example, prefers a certain return to an equal but uncertain return, and mathematically we describe that as the first derivative being greater than 0 but the second derivative less than 0. With a risk taker, we get a strictly convex utility function, so one that bows down towards the low. As you go out, it has that curve like this, okay? Whereas with the risk averse one, the curve is the opposite way. With a risk taker, you have that the marginal utility given by u prime x, the first derivative of the utility function with respect to x, is positive. Second derivative is also positive. So we see that here where we have this risk lover. The expected utility is now given by this, and we notice here that the certainty equivalent dollar amount is greater than, as opposed to less than, the expected utility amount x bar. So extreme risk lovers concentrate on upside risk and tend to be less concerned about downside risk. Risk premium is now negative because, remember, it's x bar minus xce, and the decision maker is willing to pay to take on risk. We also have two very important measures of risk aversion. The absolute measure of risk aversion, which is given by, we denote risk aversion absolute as r subscript a as a function of x. Remember, x is income or wealth. We prefer to use wealth because it makes a bit more sense. The absolute risk aversion parameter or coefficient is negative of the second derivative of the utility function divided by the first derivative of the utility function, where this is the marginal utility. The relative risk aversion coefficient, R sub R, is equal to minus the same as this one, u prime, double prime over u prime, so the second derivative over the first derivative of the utility function, but then multiplied by that value x, in other words, the place you are currently at. Now notice that these are unaffected by transformations in the utility function. Positive values imply risk aversion. The larger the value, the greater the risk aversion. And negative values imply risk taking. All right, so it's important to keep in mind, when these numbers are positive, you have risk aversion. When they're negative, you have risk taking. Now it's important to realize that this risk aversion parameter changes over time, or could. So in one case here on the left, we have that one person has greater risk aversion than the other, but only in the small. By that I mean in the small, for small levels of, remember this is income, and it depends on points x1 and x2. So at x1, a low level of income, person number 1 has greater risk aversion than person number 2, but at a higher income, person number 2 has higher risk aversion, is more risk averse than person number 1. In the case on the right, person number 2 is everywhere more risk averse than person number 1, and we call that risk aversion in the large. Now we also have various kinds of utility functions that we need to consider. So here we have a linear utility function. Remember, no risk aversion here. Here we have an exponential function where we do have risk aversion. A quadratic utility function where we have risk aversion for up to this point at least. And then we have that utility begins to decline, as a matter of fact, as you give more income, which is probably not realistic. We have absolute deviation, where we get a disaster or target level of income, and above it, what happens is you change the rate of increase in the marginal utility. Semi-variance is at the disaster level, you get a straight line again, and prior to that you've got this concave function. And then finally the safety first one, which I've worked with in several projects. Once you reach the disaster level, you're much more interested in getting income than you did up to that point. So you want to ensure that you get to this disaster level and don't fall below it. And that's indicated, of course, by the higher utility you gain once you're past that disaster level. The moments of a probability distribution of income are important. All right, here we have two individuals, and the variance and the mean rank A and B equally. So the variance of A, the mean of A is given by mu A. This is standard notation that is used in statistics, or at least in economics, that this is that refers to the mean. So the mean of A and the mean of B are identical, and it turns out that if you calculate the variance of A is equal to the variance of B, although it doesn't seem right away that it looks like that, but you'll see that this one is skewed to the left, A is, and B is skewed to the right. While skewness is measured by this third moment, and here we see that the third moment, A's third moment, its skewness is less than 0, and B's is greater than 0. So what we do is we see that skewness ranks B over A. In other words, B would be preferred, because B does not want to hit that disaster level of income. Consider chance of loss as a risk constraint. All right, so here we get the probability that X falls below this disaster has to be less than or equal to some small amount. Now kurtosis, so we've talked about skewness as the third moment. Kurtosis is the fourth moment. There also exist higher moments, although this depends on the functional form of the probability density function. So remember, these are levels of income, and we get the distribution of utility from these, okay? So that tells you how often you're within these net incomes. Okay, here we have a risk constraint where the probability that X falls below D is some small amount. D is the disaster level. In this diagram, the mean of A is less than the mean of B, and the variance of A is less than the variance of B. So the chance of loss ranks A as riskier than B, while the variance ranks B as riskier than A. So, all right, so you see here, because of this disaster level, A is ranked as being riskier than B, but when you look at this variance, even though B is always going to be higher, it ranks B as riskier than A. But of course, everyone in the room will know that you want this one, you prefer this distribution over this distribution, or one would think you would. Okay, the power utility function. Decreasing absolute risk aversion, but constant relative risk aversion. Remember those two equations. We have absolute risk aversion is U prime X over, U double prime X over U prime X, and the relative risk aversion multiplies that by X. So here we have a utility function. X is raised to the power 1 minus lambda, and then divided by 1 minus lambda. In those circumstances, U prime of X is equal to X to the, well, it's basically 1 over X to the power lambda. The second derivative is minus lambda, X to the minus lambda minus 1. So as a result, we can calculate the absolute risk aversion coefficient as being lambda over X, and the relative risk aversion coefficient as being lambda. Okay. Now, we also have the exponential utility function. Remember, these are different utility functions that we specify for various kinds of individuals. So the constant absolute risk aversion, the absolute risk aversion is constant, but increasing relative risk aversion. So we got constant absolute risk aversion and increasing relative risk aversion. So in this case, U of X is equal to A minus B e to the minus lambda X, where B and lambda are both positive. In that case, the first derivative is given by this, and the second derivative by this. Then we can again calculate the absolute risk aversion parameter as lambda, and the relative one as lambda times X. The final type of utility function that we consider is a quadratic utility function, which is both increasing absolute and relative risk aversion. In this case, the utility function is written as U of X is equal to X minus 1/2 lambda X squared, where lambda is positive. Then we find the first derivative of the utility function is simply 1 minus lambda X. The second derivative is simply minus lambda. Consequently, the absolute risk aversion coefficient is given by lambda over 1 minus lambda X, and the relative risk aversion coefficient is determined as lambda X 1 minus lambda X. And both of these, when you take the derivative, the first derivative of both the risk aversion coefficients is greater than or greater than 0. Now, the reason we use different utility functions is we try to mimic as best we can how the farmer or decision maker would deal with utility instead of expected return. So essentially, we use these different utility functions to determine how we might model these risk attitudes, because there are many ways to model risk attitude. Economists have come up with conditions that decision makers should meet if their decisions are to be considered rational. The expected utility maximization hypothesis or procedure is considered a benchmark in this regard, although many decision criteria actually fail to meet its requirements. Nonetheless, we will adopt expected utility maximization as the benchmark. So with this as background, let us look at various decision rules. First of all, maximization of expected net return or expected utility. Question: does a decision rule violate the expected utility maximization or EUM hypothesis? As we show in the next slides, expected revenue maximization does in fact satisfy the expected utility maximization hypothesis. For a linear utility function, expected utility leads to the same outcome as expected returns. So let's look at expected return maximization. So the equation that we write is maximize over the decisions J, your expected returns. So you have to pick the J, the activity set, that maximizes this probability of ij xj for the sum over all outcomes, all right, and all actions. So J refers to actions, I refers to outcomes. Usually we will pick one of these J's. So Pij is the probability event I occurs and action J is taken. Xij is the payoff if event I occurs and the action J is taken. The decision maker generally maximizes expected utility rather than expected net return. So let's look at expected utility maximization. Now we want to maximize the expected utility rather than return. So we're again maximizing, we're choosing that J, that activity that's going to maximize this part here where it's the probability of Ij times utility of Xij. So the expected utility is given by this function here, where Si is the state of nature, Aj is the action J that we take, Xsiaj is the outcome, so this is the outcome, and then Psi is the probability Si occurs. Note that in these slides, X sometimes denotes a decision, not an outcome. All right, so here it represents an outcome. In other places, we've used it to represent decision. Then we come to mean variance analysis, or EV analysis. Let's look at some background. A Taylor series expansion about the mean mu j gives this function here, mu j sigma, the third moment, which is skewness, the fourth moment, which is kurtosis, and so on. So you got the mean, the variance, the skewness, and the kurtosis that you're looking at. Expected utility maximization works only if expected utility has two moments. In other words, we can't have skewness or kurtosis. That is only if the utility function is quadratic or net returns are normally distributed. With only two moments, the expected utility of J is a function of the mean of the J's and the variance of each of these J's. So think of it this way. You've got all these outcomes and you're looking at the mean of those outcomes for decision J. And for decision J, you also have variance of these outcomes. In contrast, if utility is linear, there's only one moment. All right, so here We just have that single moment that we're concerned about. Variance or standard deviation simply measures dispersion of net returns and is defined as sigma squared, which is equal to xi minus the expected xi, or the mean, all squared, and then summed over all possible activities, or outcomes rather. Of course, you're multiplying these by the probabilities over here. So the problem with variance Vx, or sigma squared, is that deviations above the mean are penalized the same as those below the mean. And that's kind of odd, because if you earn more, you penalize the same extent as if you were to earn less than that average. Consider again the exponential utility function and normally distributed net returns. Does this satisfy the expected utility maximization hypothesis? Well, we're going to show that it does. And that's what this slide is about. So we have a utility function that's a minus b e to the power minus lambda x. B and lambda are greater than 0. We have an exponential utility function. If x is normal, then the maximum of the expected utility is equivalent to maximizing this here. Okay, and that we know that from from a paper. In essence, we can write the expected utility function as expected utility e of x minus 1/2 lambda v of x. All right, from this part here by a transformation. Since there are only two moments in this expression, expected value, or pardon me, the EV, the mean variance, applies when maximizing an exponential utility function and assuming normality of x. A normal distribution is fully described by two moments, the mean, E of x, and the variance, V of x. We have already showed that lambda is the degree of risk aversion in the case of the exponential utility function. That is, absolute risk aversion is equal to lambda. Maximizing the expected utility gives E of x minus 1/2 lambda V of x. We're given lambda. We have the expected variance decision rule. It provides an ordering of alternatives consistent with the expected utility maximization hypothesis. Where lambda is unknown, the expected variant, or pardon me, the mean variance criterion can be used to order risky choices into efficient and inefficient sets. The mean variance efficient set is also consistent with the quadratic utility function. So we can work that same thing out and we come to about the same result. And the variance is now an appropriate, or has to be considered, an appropriate measure of risk. And students can figure this out, but basically the point is that the mean variance efficient set is also consistent with this quadratic utility function. So we've got an exponential utility function and a quadratic utility function. Now there are two versions of the mean variance model, one by Freund and one by Markowitz. We're just going to look at those. The Freund approach is to maximize expected returns minus 1/2 times this risk aversion coefficient times the variance, subject to technical constraints and a non-negativity constraint that all activities have to be greater than 0. So think of this as being perhaps these technical constraints, and then X might be your choice of what to plant on what acres. So lambda is that Arrow-Pratt risk aversion coefficient. R is a function of the decision vector X. And if lambda is unknown, we could vary lambda and solve the program for its various values. So we can change this lambda and solve the program over and over again to determine how it changes. In this case, we end up with an expected, mean variance frontier. between here's the mean, here's the variance, and the indifference curve is this utility as a function of returns. With a risk-averse person, we get an indifference curve that is represented by this blue tangency. With a risk-neutral person, it's represented by the green tangency, and with a risk lover with the red. So you'll see that the choice that one makes depends on how or what their risk attitude is going to be. Quadratic programming has sometimes been referred to as risk program because mean variance analysis requires use of quadratic programming. The Freund method of the previous diagram employs an elicited risk parameter to identify the optimal point on the mean variance frontier. So what you do is you ask decision makers about their risk, and from that you're able to get a risk parameter. Now the alternative approach that does not elicit these risk parameters is this Markowitz approach. And the Markowitz approach is to minimize the variance subject to the mean of your income greater than or equal to some k, which is varied in some iterative fashion to trace out the set of risk efficient, so minimum variance solutions. And we see that in the next slide. Again, x is the vector of activity levels or decision variables. So here we have the set of all feasible plans. This is our efficient mean variance boundary, and we have increasing utility in this direction because you're increasing your mean return, and you have your variance here, and you want to reduce variance and increase returns at the same time, which implies you're moving up in this direction. The linear programming solution is no risk, which we identify as this point here, and we can end with this as we do not know the decision maker's utility function or trade-off between expected returns and variance of returns. The Markowitz approach cannot identify the optimal plan Q. The LP, linear programming solution, is obtained by maximizing expected return. Here's your expected return, because variance requires a quadratic, which would result in a nonlinear objective. So the linear programming solution can only give the highest expected outcome. So in essence, trying to determine how you're going to solve a problem that involves variance, that involves risk and uncertainty, becomes particularly problematic, and there's a lot of different methods that have been studied and tried. I have been playing around with what is called as fuzzy set theory to try and get at that, but there are many other different ways of tackling this particular issue.